Okay, today we're going to talk about rates of change. The rate of change of a function is actually called the derivative. That's actually the instantaneous rate of change, and we'll talk a little bit more about that. This I'm not sure if that's your assignment number, but for this year it is. And your essential question, what is the difference between average and instantaneous rates of change? How do you find instantaneous rates of change numerically, graphically, and algebraically? And there's a whole lot that's going on in this lesson, so it's going to take a while. We're going to split this up over a couple days. Okay, so suppose a bird, this little graph right here, this is just straight out of your book. Suppose a bird takes off from ground level at time x equals 1. So here it is right here. It's at ground level, and it's taking off, and this would be 1 right there. 1 second. It climbs for a while, then dives for a while. So it climbs for a while, then it dives for a while, then it starts to climb again. And figure 16.3 shows what its height, f of x in feet, might be as a function of time x in seconds. Now, for me, the first thing I always do is I label my graph. So they haven't given me a lot of information here. They've given me that f of x is in feet, but I need to know that that's the height of the bird. So I'm going to write height on there. I promise you're probably thinking, Ms. Frisk, this is so simple, of course. I promise this is going to be very helpful if you label your axes. Okay, and then this is x in seconds. Okay, so this is feet, and this is seconds, or this x-axis is time, right, in seconds. Okay, and if that stuff's not labeled for you, make sure that you do that. So now we know that the bird's height, which is depicted in this graph, is given by this cubic function right here. So we're going to keep coming back to this cubic function. So we're going to need to know where that's located. Now, anytime that we're talking about rates of change, we're actually talking about, there's this formula that you probably learned sometime in like Algebra 1 or something like that. Distance equals rate times time. Okay? Well, if we want to know what the rate is, then we have to take the distance and we have to divide it by time, right? So basically, anytime we're talking about rate, distance divided by time will give us the rate. So if we want to know how fast this bird is going, well, we can't really tell that from this graph. But what we can do is we can find some rates of change where we basically take the height and we put it over the time, right? So if I, for example, take this height in feet and divide it by, right, so that's distance, divide it by time, which is in seconds, right, I get feet per, I'll just put second, feet per second. And feet per second is a rate. It's actually a rate we call velocity, right? How fast is this thing going? So you've been dealing with velocity for a very long time. You just haven't been able to find the exact velocity at an instant. And that's what we're going to talk about today. Okay, so I would get out a highlighter. You're also going to want your calculator. You're going to want a lot of stuff. But right now I think highlighter, calculator, pencil, you should be good. All right, so I went ahead and gave you these properties first. So I'm going to focus on the top half of this box right now. So I'm just going to kind of break this up into 2 sections because you know this part right here. Average rate of change. We have been dealing with average rate of change since the moment I met you. Okay, average rate of change. Average rate of a change of a function over an interval starting at x equals c is the change in the y values of the function divided by the corresponding change in the x values. Okay? Does that sound familiar to you? Change in y over change in x. So, for many, many years, we have looked at this actually linearly. So I'll go ahead and I'll draw a linear function here. Here's my linear function. We'll call this, well, it doesn't really matter. This will be my x. This will be my f of x. So anytime I was looking for a rate of change, right? Let's say this was height in feet and this is time in seconds. Okay, so this is feet, and this is seconds. And if I wanted to find the velocity, I could basically take 2 points on this graph, and I could say, here's 1 point, I'll call that, how about C? Here's another point, I'll call that one X. And their corresponding outputs, well, this one would be f of C, and this one here would be f of x. And I could find the rate of change between the two by basically doing f of x minus f of c, right? Change in the y's, over x minus c, change in the x's. And right there, that's what gave me, wait for it, this is basically slope, right? So this is the same thing as y2 minus y1 over x2 minus x1. We've been doing this forever, right? Okay. So really, the average rate of change, that's the same exact thing as slope. You've been doing that for a very, very, very long time. Okay, now in a function, this slope, well, I should say functions are not always linear, right? So let's turn the page over. We'll come back to that other page, but so in this curved function, it's not going to be so easy to just find the slope and have it actually be the rate of change over a certain specific amount of time. So we call that the average rate of change because it's not the actual slope of this curve, okay? Instead, what it is it's an average between two time intervals, and here it's between time 2 and time 3. And so really, when you're finding the average rate of change of a function or the slope of a function, you're really finding the slope of that secant line, okay? So this line right here is a secant line, meaning it goes through 2 points in the curve, okay? The slope then gives you the average rate of change. So back to that other page. We're going to flip back and forth a couple times. Graphically, so down here, graphically, the average rate of change equals the slope of the secant line. So the average rate of change is the slope of the secant line. That contains those 2 points, just like, similar to what I wrote here, but this was a linear function. So just showing you that this can be applied to any curved function, and it'll give you an average rate of change. This, in a linear function, is going to give you the actual rate of change because you're going to basically go rise, over, run, and you're going to have that slope triangle. Okay, so we're going to do a couple things here, but why don't we find, I think I'll just write it right here. We're going to find average and instantaneous rates of change of the bird's height from x equals 2 seconds to x equals 3 seconds. Okay, so right now we've just covered average rate of change. Let's go ahead, let's turn the page, and let's go ahead and find that average rate of change. So this one, I'm going to kind of divide these into 2. This is going to be my average rate of change. I'll use the little delta symbol for change. All right, so the first thing you want to do whenever you're dealing with average rate of change is you need to know your x's and your y's, right? So I'm going to make myself a little input-output table. This is the same exact graph. We were already given the function for that graph. So in order for me to evaluate, now the fastest way to do this is to go and create a function in my calculator that I can then use my table for the values, right? So I care about the average rate of change between 2 seconds and 3 seconds. So those are my inputs, and then I'll get my outputs for those. So the function was, back here, x cubed. Please make sure that you're doing this with me. Minus 13x squared plus 52x minus 40. Okay, so that's the function I'm putting in. I'll start my window at 2, and I'll just go up by 1 because I just need the outputs for 2 seconds and 3 seconds. So it's 20 and 26. So now I can find my average rate of change. Which is basically just my slope, right? So that's going to equal 26 minus 20 over 3 minus 2, or 6 over 1. And what are my units here? Again, units were feet per second. So I'll just say that this is 6 feet per second. Or you could go back up here and say, hey, this is feet per second. And same thing here, feet per second. The units become really important because now I know that my rate of change is a velocity. Sometimes your rate of change will be an acceleration. Okay, we were given a displacement function, right? What's its distance from the ground? This is a displacement function. When you take the slope or the rate of change of a displacement function, you end up with a velocity. And when you take the rate of change of a velocity function, you end up with acceleration. And then we'll also go backwards, but we'll save all that for next year. Okay, so now let's talk about instantaneous rate of change. Back to the front page. So the instantaneous rate of change, so let's talk about instantaneous. So what is an instant? What is an instant? Like, oops, I'm not even on the page anymore. Sorry. One instant is right now. Like it just happened. The instant just occurred. So there is no change in time in an instant, right? So basically there is no change in time. You can think of it as like 0 seconds. Well, imagine finding the slope when x doesn't change at all. So you'd have x minus x. So you're going to be dividing by 0. That's going to create an undefined number. Okay, so you've got a problem there. So for the instantaneous rate of change, I'll use a different color just for fun. The instantaneous rate of change is actually what we call the derivative. And we can find it, we actually can. It's the limit of the average rates of change as x approaches c. So it's this right here. Okay, so it's the limit. Let's see, I'm going to go ahead. I think I should highlight these. So I'm going to go back and highlight my pink one too. I'm going to highlight both of these. So basically you take the slope, but you need the limit as x and c get closer and closer and closer together. So if x, for example, is 2 seconds, right, then I'm going to want to find c values that are close to x, but not exactly x. So maybe 2.1 seconds, or 2.01 seconds, or 2.0001 seconds, and so on. Now, graphically, instantaneous rate is happening in an instant, right? So you can't have the secant line. I'm going to flip back over a couple more times. You can't have the secant line where time is changing, right? Time is not changing. So if I care about it 2 seconds, right? Then I just want to be at that one point. So anytime a line intersects a function at one point, we call that a tangent line. So really, instantaneous rate is the slope of the tangent line. So this one right here is the instantaneous rate of change. And we really care about this tangent line. And we care about its slope. The slope of that tangent line is going to be the derivative. Okay, it gives a more exact number of what that instantaneous rate of change is. Because really what's happening is that tangent line and the function, if you zoom really close on that, they have the exact same slope. And we can get that slope by finding the slope of this tangent line. Now I'm going to do this problem for example 1. So this will be done in example 1. We will do in example 1. Okay, so I'm going to wait a little bit on that. Okay, we're going to do that one kind of last. Okay, so let's come back over to the front page one last time. So much flipping, I know. So graphically, the instantaneous rate equals the slope of the tangent line. The instantaneous rate equals the slope of the tangent line. To the graph of function f at that point, right? At the point that it's touching it. Okay, so it's just touching it at one point. That's the definition of tangent line. That's something that we learned back in geometry. And if you are confused about secant line and tangent line, and you still don't understand them from my pictures, by the graphs that I've given you here, then please, please, please look them up. But one more time, secant line touches a function in two spots. So we have 2 points that we can then find the slope of. A tangent line does not. It touches the function in only one spot. So in order for us to find the slope here, it's actually the slope of the tangent line is going to give us the derivative. Okay? So slope of tangent line. This is slope of secant line, slope of tangent line. Okay, let's start doing some math. Now, there are many ways to approximate the derivative, or the instantaneous rate of change, right? How fast something's going, or whatever the rate of change is at an instant, at time being 0. Or the change in time being 0, I should say. All right, so one way is to estimate it numerically. So to estimate the instantaneous rate of change at x equals 2 seconds, the first thing you're going to do, so let's see. So why am I saying 2 seconds? Well, we're trying to find, we already found the average rate from x equals 2 to x equals 3 seconds. Okay, now we're going to try and find the instantaneous rates of change, basically at x equals 2. Okay, we can do that for x equals 3 as well. So let's go ahead and do it at x equals 2. Okay. So the first thing we'll do is we're going to find the average rates of change over smaller and smaller time intervals. Right? Because if I'm talking about finding the rate of change at x equals 2, then I can't be very far away from 2. Okay, so I'm going to find it at like 2.1, and then getting a little closer, 2.01, and a little bit closer, 2.001, and a little bit closer, 2.0001. I think I said that right. Okay, so that's the first thing I'm going to do. So right here, I'm just going to make myself an input-output table. Actually, I'm going to do input, which is x. Then I'm going to do output, which is f of x. Then I'm actually going to do the average rate of change. Which maybe you forgot, but basically what you're going to do is you're going to take your f of x minus f of some number that we care about. So f of x right now for us, right now we care about 2. So f of x will be numbers getting closer and closer and closer to 2. Okay, and then we're going to put all of that over the x minus c. Basically, we're just finding the slope. Okay, so we're going to start with, actually, I'm going to put 2 down at the bottom. Let's make sure I give myself enough room. Go down further. Give myself lots of room. So we'll do 2 at the very bottom. Okay, so now close to 2 is like 2.1. But even closer is like 2.01. And even closer to that is 2.001. And even closer to that is 2.0001. Okay, so this is my first step. So I already have my function in my calculator, right? Because we're just modeling the bird. But notice that my table of values isn't very helpful to me. It's starting at 2, and now I'm going to have to say, well, could you please increase by 0.1? And every time I do this, I'm going to go on to the actual number. I'm going to get a little bit more exact number. So this is 21.131. That one was the exact same, but they will change. So let's add to the hundreds place now. So now this one is 20.119. Okay, let's go to the thousands place. Okay, so maybe I didn't give myself enough room. 20.0. I'm going to use significant figures, so I'm going to go all the way to like the 9s. 20.1199. And then I'll do, what is that, the 10,000s place? And they go over there because otherwise they're all going to be the same. Oops, you guys can't see that. Otherwise they're all going to be the exact same number. So I go and I click on it and I can see that I'm getting 20.0011 and then 3 9s. I'll go off my page just a little bit, or off my column a little bit. Should have made that one wider. And then at 2, I already did that. I did that up above. So the output is 20. So you can see that, as I get closer and closer and closer to 2 seconds, it's getting closer and closer and closer to 20 as 20 feet for its height. But now we have to actually find, because I said find the average rate of change over smaller and smaller and smaller time intervals. So we actually need to find the average rate of change, which I haven't done. So we'll find the average rate of change from 20 to 21.131. So, or sorry, from 2 seconds to 2.1 seconds. So that's going to be, I'll take the bigger number, 21.131 minus 20 all over, and then that's 2.1 minus 2. Or in other words, if you subtract these, you get 1.131 over 0.1. And to get rid of this decimal in the denominator, just move the decimal over 1, so I do the same thing up here. So this is approximately 11.31. Nope, I lied. 11. Yeah, no, that's right. 11.31. And that's feet per second. Okay, and I'll do that for each one of these. So now I'll do 20.119 minus 20 over, and then the change in the x's, which is 2.01 minus 2. So I'm getting, let's see, 0.119 all over 0.01. Move my decimal over 2 places, so I just have a 1 in the denominator. So that's going to be approximately 11.9 feet per second. Okay, do this a couple more times. How about, I don't think I need to keep writing this out. Hopefully you guys you're seeing the pattern. Subtract the y's, or the outputs, and you get 0.01199. Subtract the inputs, and you get 0.001. Oops, and I'll put an approximation sign. To get 1 in the denominator, I move my decimal over 3 places. So that's 11.99 feet per second. Okay, and I'll do one more here. The average rate of change between 2 seconds and 2.0001 seconds. Well, if I subtract these, I get 0.0011999 all over 0.001. Nope, one more zero. There we go. To get 1 in the denominator, move my decimal over now 4 places, which gives me approximately 11.999 feet per second. Okay, so we found all the average rates of change over smaller and smaller time intervals. And now the second thing we need to do is we're going to take the limit of the average rates of change. Take the limit of the average rates of change as the time gets closer to 2. So really what we're doing is we're saying what's the limit as x approaches 2 of f of x minus f of 2. F of x was whatever we chose, right? We chose a whole bunch of different values for x all over x minus 2. And when we do that, well, what's this approaching? I start at 11.31 feet per second, go up to 11.9, 11.99, 11.999. This appears to be getting really, really close to 12. So I'm going to say right now my estimate is it's approximately 12 feet per second. And that's me estimating it numerically. Numerically means taking a table of values, finding average rates of change, and then finding the limit of those average rates of change as you get closer and closer to the time that you care about. Or in other words, as the change in time goes to 0. So notice, right, my change in time from 2 to all these different values kept getting smaller and smaller and smaller, meaning it was going to 0. Okay, so this is my final answer for estimating numerically the derivative or the instantaneous rate of change. Algebraically, now this is my favorite way to do this. Well, I got an even easier way, but this one's pretty cool. And this involves some algebra that we haven't used in a while. So if I wanted to find the instantaneous rate of change at time being 2, I can call this is called f prime of 2. This little symbol right here means the derivative. That's basically your derivative symbol, okay? F prime of 2. And it's just like a little apostrophe, okay? And this, based on our definition that we have on our first page, f prime of anything, right, any value that you want is going to be the limit as x approaches that thing of f of x minus f of that value over x minus that value. So maybe I should write that up here. So this will be the derivative f prime of c is equal to, the limit as x approaches c of f of x minus f of c all over x minus c. Okay, so let's see what this looks like when I do this with 2. So f prime of 2 then will be the limit. Wherever I see a 2, that's going to replace the c's, right? All these c's get replaced with that 2. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Now, if I went ahead and I evaluated this limit, and I plugged 2 in for x, notice I'm going to get 0 over 0. We actually call that the indeterminate form. But right now, just focus on the fact that 2 minus 2 is 0. You can't have a 0 in your denominator. You've got a problem there. You can't really go forward. But we're going to move forward a little bit further. Now, f of x, I'm going to keep this limit. The limit as x goes to 2. We have a value for f of x. F of x is the function we were originally given. Back to that first page. That's my f of x. I'm going to plug this in for f of x. So instead of f of x, I'm going to have x cubed minus 13x squared. I'm just copying it. Plus 52x minus 40. Okay, so that's f of x right there. That came from page 1. That's basically the displacement function for the bird. And then from that, I have to subtract f of 2. So I am now going to subtract, well, f of 2, we've done that. We did that right here. F of 2 is 20. So from that, I'm going to subtract 20. And I'm going to put that all over x minus 2. Simplifying this a little bit further, the limit, I'll just combine like terms. I've got x cubed minus 13x squared plus 52x minus 60 all over x minus 2. That's great. Still no help, because if I go ahead and I plug 2 in, it doesn't matter what's on the top. The bottom's going to be 0. Can't divide by 0. It's undefined. However, what I can do is I can see if this is a removable discontinuity. If it's a removable discontinuity, then I'll still have a limit. Now, if this is not a removable discontinuity, so I'm going to see if it's a removable discontinuity by using synthetic division or synthetic substitution, because it's x to the first power. If it wasn't x to the first power, if it was x to some other power, I would have to use long division. Okay? Luckily, I don't have to do that right now. Now, if it's not a removable discontinuity, then that means it's a vertical asymptote. And that probably means, or definitely means, I don't have a limit. Okay? So if it's a removable discontinuity, I could have a limit. If it's not, if I can't remove it, then I have vertical asymptote, not a limit. The limit won't exist. So what I'm going to do now is I'm going to come over here, and I'm going to do some synthetic division. So set x equal to 2. Right? Because if I set that equal to 0, then x would equal 2. So I'm going to divide by 2. Let's see. Every single exponent is accounted for. So I've got just my coefficients. 1, negative 13, 52, and negative 60. Bring down the 1. I get 2. That's negative 11, negative 22, positive 30. And in fact, I get a remainder of 0. So x minus 2 is a factor of this junk. Maybe I could have done it factor by grouping. I'm not sure. I'm not even going to try it. Okay. And now I'm left with, well, this is my constant. This is x to the first power. This is x squared. So now, after I've simplified this, I can now evaluate. That should not give me any problems. Okay, so again, because this was 0, remainder of 0, I knew that this was a removable discontinuity, meaning it's just a hole. Okay, so that means that it's going to be approaching, the function will be approaching the same output from left and right. So the limit does in fact exist. And I can now plug 2 in. So I'll have 8 here and 4 there. That's going to give me 12. So right now, 12 feet per second appears to be my instantaneous rate of change, or the velocity, at x equals 2 seconds. which was exactly the same as the way that we did it numerically. Not the same as the average rate of change, right? That average rate of change between 2 and 3, well, that is way too big of a gap, and we're getting 6 feet per second. The instantaneous rate of change is the slope of this tangent line, which is much steeper than the slope of the secant line, and hence it is 12 feet per second. And we're proving that again and again by doing numerically, algebraically, and now we're going to go ahead and deal with this graphically, just like I said we were back here. Well, that we would do this instantaneous rate of change in example 1. Okay, so example 1 wants you to find a particular equation of the line tangent to the graph of f of x, basically our same function that we've been using that models the displacement of the bird, or the height of the bird, at the point where x equals 2. So basically what we're doing is we're trying to find the equation of this tangent line right here. Plot the graph of function f and the tangent line on the same screen. Zoom in on the graphs at the point where x equals 2 and record what you observe. Okay, awesome. So, first of all, we know that the equation of a line needs a couple of things. Now, if you were using, for example, slope-intercept form, you would use y equals mx plus b. Okay, so you would need the slope, and you would need the y-intercept. Another way that you can do this, and I bet your book is going to do this, because our calculus book uses point slope a lot, is instead of using a y-intercept, it uses a point. So you take y and you subtract from that y1. That's the y value of a point that you've been given, equals your slope, x minus x sub 1. And that's the x value of a point that you've been given. Either way, you need to know your slope, and even to get your y-intercept, you're going to need to know a point. Okay? So, for both of these, let's see. The point that we know, I'm going to keep going back to this graph. The point that we know is that we care about when x equals 2. Well, when x equals 2, we already know that f of x equals 20. So I know for a fact that f of 2 is equal to 20. Or in other words, I have this point 220 that's going to be on the tangent line. Okay? Second thing I already know, because I've already figured it out, going back to my very first page, the instantaneous rate equals the slope of the tangent line. So I know the slope of the tangent line because I have found the instantaneous rate of change at x equals 2 twice. I have found it both algebraically and I have found it numerically. And both times I got 12. This was an approximation. This one I actually found algebraically. It is exact. So I know that my slope, which is going to be the same as f prime of 2, which by definition is the same as the limit as x goes to 2 of f of x minus f of 2 over x minus 2, I know that that's 12 feet per second. So I just rewrote everything that we've talked about right here. Okay, so I have my slope and I have a point, and I can easily put this into either form that I care about. I'm going to go ahead and use point slope form. You're more than welcome to use slope intercept form. You already know, I know you have lots of practice with this, maybe not so much practice with this. So I'm just going to go ahead and use that one that you don't have as much practice with. Okay, so I now take my point slope, okay, and I basically say y minus, okay, the y value that I know, which is 20, equals my slope, which is 12, times x minus x1, which is from the point that I know, which is 2. Sometimes they'll leave it like this. Other times they'll go ahead and they'll add the 20 to the other side. So you might look at it, if I distribute 12x minus 24 plus 20, or y equals 12x minus 4. That right there is the equation of the tangent line. So now we'll go ahead and we'll plot the graph of the function and the tangent line. And we'll record what we observe. So I've already got the graph. Now I'm also going to put in my tangent line. At the point 220, that's really what I care about, so I should make sure that my window is including 220. That's a little big. Let's go 50. I'm going to graph them. And what do you notice? Notice that this point appears to be tangent, or sorry, I should say the tangent line appears to be tangent to the original curve. I can double check that by calculating the point of intersection. So on the second trace, first curve is my blue one. Yep. Best guess. Look at that. 220 appears to be the point of intersection, or is in fact the point of intersection. So let's see. Zoom in on the graphs at the point where x equals 2 and record what you observe. Well, I observe that. Let's see, am I on the screen? The tangent line and the function intersect at 220, which is a point on the function. Another thing that you should observe is if you zoom in here, these two graphs are going to look like one and the same. So let me zoom in. I'm just going to zoom in there. Look at how much they look like they're exactly the same. So the slope of this tangent line right there really is in fact the slope of that curve at that point x equals 2, or at x equals 2. Now we call this local linearity, which basically means the more and more you zoom in on this point of intersection of the tangent line and the function, they're going to appear to be the same line. Okay, so that's another thing I'm going to say. I'm going to say at this point, both the tangent line and the function appear to be the same line. We call that, this is not something you need to know this year, but we do call it local linearity. Okay, so we're going to now look at doing the algebraic derivative of a power function. And when I spelled this wrong. And when I do this, I'm going to show you that it takes a really long time to always do it this way. So instead what we're going to do is we're going to derive. So I said deriving. I don't think that's spelled right. So just have one I. We're going to derive the power rule. This is a rule that's going to help you so that you don't have to, every single time when you need to do the derivative, do a whole bunch of synthetic division. Okay, so this is going to be kind of a shortcut, but we're going to derive that shortcut. It's going to take us a little bit of time to derive. Okay, so if I told you to find the derivative of a power function, so like f of x equals 7x to the 4th power. At the point x equals 5. Okay, so what you do is you think about the definition of derivative. So you'd say f prime of 5 will then equal the limit as x approaches 5 of f of x minus f of 5 all over x minus 5. And then you'd go forward and you'd say, okay, well, that's really the same as the limit as x approaches 5 of f of x, which is 7x minus 4, minus f of 5, which is really 7 times 5 to the 4th, all over x minus 5. And then you'd say, okay, let me go ahead and evaluate this. So what's going to end up happening here, I'll go one more step before I evaluate. So just so that we can simplify this, this ends up becoming 4,375. Okay, so what happens here? Well, I plug 5 in, and guess what's going to happen? I'm going to get an undefined number, an indeterminate form. So I'd have to go to synthetic division, and that does, it takes a while. And there's times for that, but there's also times where we want to make this go quicker. And I can take the derivative of this super quick, and I'm going to show you how. But before I do that, I'm going to prove it to you, okay? Or I'm going to derive it for you. So let's say instead of using 5, let's use any constant. Okay, so we're going to use just c to represent constant. So f prime of c, right, and this is a constant, like 5 or 2 or 10 or any number you want. Well, that'll be equal to the limit as x goes to c of f of x minus f of c now over x minus c. Okay, so then what I do is I would go ahead and I plug in my function. Okay, so now this is going to be the limit as x goes to c of f of x. Well, instead of f of x, it's 7x minus 4, because, or sorry, 7x to the 4th, because that's actually what the function is. And then, instead of f of c, we're going to actually plug, like here it was f of 5, we plugged 5 in. So now we'll actually plug c in. So this will be 7 times c to the 4th, all over x minus c. Okay, I'll simplify this a little bit, just to make it a little bit easier. So the limit as x approaches c, in the numerator we've got a 7, which is a common factor. I'll factor that out. Okay, and now I'll do synthetic division, and I'm just going to do it on this piece right here. So I'll leave the 7 out, and then I'll go back through and I'll multiply that once I'm done. Okay, so I'm going to say, set this denominator equal to 0, so x equals c. So I'll do synthetic division with c. And then I've got x to the 4th all the way to my constant. Okay, so I need to make sure that I put zeros in for x cubed, x squared, and the x terms that are missing here. So my coefficient of x to the 4th is 1. Coefficient of x cubed is 0. X squared, coefficient 0. X coefficient 0. And then my constant is negative c to the 4th. I could have done this just like up here. And, it would basically look very similar. You'd have a 7 here, but then you'd have a bunch of zeros, and then you'd have 4,375 right here. But I'm doing this so that I can derive this, what we call a power rule. Okay, so I bring the 1 down, that leaves me with c, add those together, that's c, multiply those, I get c squared, add, I get c squared, multiply, I get c cubed, add, I get c cubed, multiply, I get c to the 4th. Okay, and that tells me that basically x minus c is a factor of x to the 4th minus c to the 4th. Okay, so at this point then, what I'm left with is the limit as x approaches c. Well, I still have a 7 here. Okay, so it's going to be 7 times, okay, now this is going to be my my constant, right? And then this is going to be x to the 1st power, x to the 2nd power, x to the 3rd power. So I'm going to have x cubed plus, c is my constant, or coefficient in this case. So c times x squared plus, and then I'll have c squared times x, and then I'll have c cubed, which is just my constant, all over nothing because we already divided out the x minus c. So now I can go through and I can evaluate this. So everywhere where I see an x, I'm going to put a c. So now this is really 7 times, well, instead of x cubed, I'll do c cubed. And then I'll have a c times plus a c times a c. Now this becomes c squared. Plus, now you have c squared already times, and then for that x, I'll put in a c. And I think I should have put a plus sign here. Not a multiplication, sorry, it was positive. Plus a c cubed. Which ends up giving me this also is c cubed. This term right here will also be c cubed. And this last term was already c cubed. So I really end up with 7 times, well, I have 4 c cubes. Now let's relate this to what my original function was. Because this right here, this is f prime of c, right? Okay, so if I took, for example, this right here, notice my 7 is still part of this. Notice my power. My power has come down in front. And what used to be my power, okay, this right here, was subtracted by 1 and became my new power. Okay, so what we can learn from this, and really if I simplified this, I would end up with 28c cubed. And so if I wanted to plug 5 in, I would just put 5 there. If I wanted f prime of 5, 5 goes right there. That would give me my number. So let's see. Our power rule then says that if f of x is equal to 7x to the 4th, then f prime of x will equal 7 times, and then what you do is you bring down that 4, leave your variable alone, and then subtract 1 from that original power. Okay? And so that's basically going to equal 28x cubed. So then if we wanted f prime of 5, right? So if I end up with this, or actually the 28x cubed, then it's just going to be 28 times 5 cubed, which becomes a really simple problem. So let me go ahead and just do that real quick. Would end up giving you 3,500. So let's talk about our power rule. Okay, so the power rule is now on the next page. But this right here, let me actually just say that right here, this is us deriving the power rule. Okay, so on the next page, at the bottom, we have the power rule for derivatives, which basically says if you have any function like k times x to the n, so like 7x to the 4th, where n stands for a non-negative integer and k is a constant. I always call it a coefficient, but constant meaning that it's just a single number dilation factor. So it is actually, it's like, think of it as like your a, right? In any function, that a is your dilation factor. Then f prime of x is equal to k times n times x to the n minus 1. So let me go ahead and write that because it's kind of blurry there. So if f of x equals, you know what, I'm going to change it up a little because we always use our dilation factor as a. So a times x to the n power. Then f prime of x will be, well, you'll keep that coefficient, then you bring that power down, leave the variable where it is, and then that power gets subtracted 1 from it. So this is n minus 1. Okay, so this is your power rule, just written a little bit bigger. And I used a for our dilation factor. Power rule is super, super helpful. Okay, and so to find the derivative of a power function, multiply the original exponent and decrease the exponent by 1. So let's go back to, let's go ahead and let's use that real quick, this power rule. We're going to actually use the power rule and the sum rule for derivatives at the same exact time. So for our original flight of the bird function, we were given, on the front page, you had this function. And you wanted to figure out, at one point, the question was, you know, how fast is the bird going at time being 2 seconds, right? So basically, we want the instantaneous rate of change. And now we've gone through this and we figured this out a bunch of different ways. Numerically, by making a table of values where we get closer and closer and closer to 2, find those average rates of change and then the limits of those average rates of change. Graphically, we did it where we actually drew a tangent line and came up with the slope of that tangent line. And then algebraically, we did it where we used the definition of derivative and then had to use synthetic division to divide out the x minus 2 on the bottom. Now let's go ahead and let's use the power rule, which is going to be the simplest way. Okay, and then I need to just add one thing here. So if we have a polynomial such as this, where we have several terms, then to find the derivative, what you do, take the derivative of the polynomial, you just basically take the derivative of all the terms and you add them together. So if I wanted to find the derivative of this function as a function, f prime of x, right, where I'm not actually saying at 2, at time being 2, I'm not giving an actual input, then I do the power rule for each term. So for this term, I would bring that 3 down and then subtract 1 from 3. So this term becomes 3x squared. I bring that 2 down, so it's negative 13 times 2, or negative 26. Subtract 1 from this 2, so it's just x to the first power. This has a power of 1. Bring that 1 down, you get 52. What happens when I subtract 1 from 1? It's 0, so I have no more power at all. And then this was originally x to the 0 power. And if I bring that 0 down, I'm going to end up multiplying by 0, getting 0. So constants always just go away. They become 0. Okay, so that's the derivative function. And now what if I wanted to know what is the instantaneous rate of change, or the velocity, of this bird at 2 seconds? Well, I now have the function that I can then plug 2 into. So this would be 3 times 2 squared minus 26 times 2 plus 52. Those are opposites. They're going to go away. This right here leaves me with 12. So your actual derivative is 12 feet per second. Okay, we got one more example here, I think. Let's see. We have more. Oh, we got more stuff on the back. All right. Example 2. Given f of x equals 0.3x to the 6, find an equation for f prime of x and use it to find f prime of 2. So just like what we just did down below. So f prime of x, sorry, that's a prime. Well, it's 0.3x to the 6, so I'm going to bring that 6 down and multiply it. I'll go ahead and I'll write it out. 0.3 times 6, and then it's x, and I subtract 1 from that power to the 5th, which really is 0.3 and 6 is 1.8x to the 5th power. So now let's do that for f prime of 2. Right, so this would be the derivative function. We'll actually get to that not this year, but next year. We'll graph the derivative function. But we're not going to do that today. So now let's go ahead and we'll actually take 2 and we'll plug it in to our derivative function. So this is really 1.8 times 2 to the 5th, or 1.8 times 32, which ends up giving you 57.6. So that would be the instantaneous rate of change at 2. And I'm not sure what this is even about because they haven't given me any units. I have no idea. So write an equation for the tangent line at x equals 2. Well, the derivative at x equals 2 is this. This is the slope of the tangent line. So this right here is the slope of tangent line at x equals 2. Okay, so I've got a slope, but in order to do an equation, I also need a point. Okay, so in order to find a point, so I also need a point. I'm just going to write that down for you guys. So I also need a point. And the point I care about is when x equals 2. So I'm going to make myself a little input-output table. If I plug 2 in, that's 64 times 0.3. I'm not really sure what that is. 19.2. So my point here would be 2, 19.2. And now I can use either point-slope form or slope-intercept form. Totally up to you. I'll do point-slope form. So y minus my y1, which is 19.2, equals my slope, and my slope ended up being 57.6. And then x minus x1, or the x value of my point, which is 2. Okay, so then I'm going to end up with y equals, let's see, 57.6, 0.6x. And then distribute that, and you should end up with negative 115.2. And I'll add the 19.2 to that side. So I end up with a 57.6x minus 96. Okay, so there's the equation. Let's see, so I got a lot of stuff here. Let's go back through my question. Find the equation for f prime of x. Well, f prime of x is this. And use it to find f prime of 2. Well, this is f prime of 2, which is really the slope of my tangent line, or the instantaneous rate of change at x equals 2. Write an equation for the tangent line. Okay, I did that. And plot the tangent line and function f on the same screen, thereby verifying that the line really is tangent to the graph of the function f at that point. Okay, so we've done that before. So we're going to actually plot this graph. Let's actually see what this looks like first. And the tangent line let's see, I don't know what my window looks like. Okay, that's not going to help me at all. Okay, well, I know that f of x needs to go up to at least 19.2. I'm going to go up maybe I'm going to double that, like 40. And my x value should be 2. I think I need some negative values so I can see my x and y axis. So, and my y min is 12 for some reason. So how about I'll go negative 5. And how about we do, let's go 40 for the y max. Let's see if that gives us a better graph. Oh, that gives us a way better graph. Okay, so all right, so I'm gonna have this, because x is 6, it's got this like flatness to it, something like that. So this is f of x equals 0.3x to the sixth. And then I've got this tangent line, which basically, let's see where they intersect. How about that? And then that can give me the point of tangency. And I should know right now where they should be intersecting. Let's see, where is my, oops, I'm way down below. Which is 1.999999, very, very close to 2. And then 19.19999, which is very close to 19.2, which is exactly the point that I was looking for, right? So at 2, when x equals 2, I was looking for the tangent line, and I was looking for the equation of that tangent line. So I'm just going to put this point right here. That's the point of tangency. And then you can draw maybe with a ruler your tangent line. Okay, and then verifying that the line really is tangent. Yep, I verified it because basically their point of intersection is the point of tangency that I was looking for, was x equals 2. So the slope of this line right here is 57.6. Right? F prime of 2 is 57.6. So the slope of this line, even though it doesn't look like it, is 57.6. All right, I think I finished every, oh, no, one more. This one's not too bad. This one's pretty easy, actually. All right, so we've got figure 16-3H shows the polynomial function. X cubed minus 11x squared plus 36 minus 26. Okay, and basically I think this is our, oh no, it's not. Just a different function. Okay, assuming that the derivative of the sum, okay, let's see what graph we have. So we have this graph here. I don't really have any units. I know that x and f of x, that's basically all I got. Okay, assuming that the derivative of the sum or difference of several power functions is the sum or difference of the derivatives of the individual terms, find the equation for f prime of x. So f prime of x, all they're saying here is that you take the derivative of each individual term, and so the derivative of this function is all of those individual terms having the derivative taken of them, and then continuing with the exact same signs or whatever signs they turn out to be. Okay, so for A, let's see, just so you guys can see this on the screen, f of x is x cubed minus 11x squared plus 36x minus 26. Okay, so then f prime of x is just me taking the derivative of every single term individually. And now that we know the power rule, I'm going to use the power rule. Now there will be times where you're going to have to show that you understand how to find the derivative, not using the power rule, but potentially using a numerical table of values where you have to find, the different average rates of change and then the limits of those average rates of change. There will be other times where you're going to end up doing it algebraically because they tell you to do it that way. You have to be familiar with all the different ways to get the derivative and what the definition of derivative actually means. Okay? Definition of derivative, once again, is this right here. But other times, if they don't specify, use the power rule. Okay? Right here, they're not telling me how to do it, so I'm going to go ahead and I'm going to use the power rule. So x cubed, bring down that 3, take 1 power away. There it is. Next term, it's a negative. Bring down that 2, it's negative 22x, and then take 1 power away, so x to the first. This is x to the first already. Bring that 1 down, it's just going to be positive 36. If I subtract 1 from 1, I'm going to get 0, so I have no more x's. And then the constant always goes to 0 because x to the 0 will multiply to give you 0. Okay, A is done. B. Find f prime of 2 and f prime of 3. Okay, let's do that first. So f prime of 2. I basically just take this and plug 2 into it. You have to find the derivative first, because if you plug 2 in first, you're just going to have a constant right here. And when you take the derivative of that, that's just going to be 0. Okay, so you have to find the derivative function first. Then you plug in your 2 or your 3 or whatever they're telling you to plug in. Okay, so that's going to be 12 minus 44 plus 36, or 12 minus 8, which is 4. Okay, let's do f prime of 3. I'll do that right over here. Because it's basically the same thing, just now you're plugging in 3 everywhere that you see x. So 27 minus 66 plus 36, or 27 minus 30, or negative 3. Alright, so show that these values are consistent with the graphs. Okay, so what do these values mean? Well, I've taken the derivative, and then I found the derivative at a certain x value. So these are the slopes of my tangent lines at x equals 2 and at x equals 3. So let's see. So at x equals 2, if I were to draw myself a tangent line here, should that have a positive 4 slope? It definitely looks like it has a positive slope, right? The graph of the function itself is sloping up, so it has a positive slope. There's not much more that you can do to verify that. It looks, it doesn't look super flat. It looks like it's about a slope of 4. So we can say that the slope of the tangent line is 4, and the graph of f of x is sloping up. That's so sloppy. I'm so sorry. I'll try and be neater over here, but that's sloping. All right, and then for negative 3, so this is at x equals 3. Let's look at the graph there. At x equals 3, if I were to draw a tangent line, well, that does have a negative slope, right? That tangent line. The function itself is sloping down, and maybe it appears to be about a negative 3 slope. So here, we'll write the same type of argument. Slope of the tangent line is negative 3, and the graph of f of x is sloping down. Maybe I should write, all right, at x equals 3. Okay, so I found both of these, and then these are my explanations. C. From figure 16-3H, estimate to 1 decimal place the x-coordinates of the 2 extreme points. Okay, so let's find our 2 extreme points. Well, it appears to me that I have a max here and a min about here. Okay, so for C, where does my maximum occur? Maybe 2.5? And where does my minimum occur? Maybe 5? 5.0. They want it to 1 decimal place, but 5 and 5.0 are the same. Okay, let's do one last thing here. For D, at each extreme point in part C, the tangent line will be a horizontal line. Horizontal lines with a slope of 0, right? Because there's no rise, but you do have a run, so slope of 0. So every horizontal line has a slope of 0. Thus, the derivative will also equal 0. Okay, so because that tangent line, right, if I were to draw a tangent line right here, it's going to be horizontal. Tangent line up here, horizontal. Slope of the tangent line is 0. Okay. Find the x-coordinates of these 2 points by setting f prime of x equal to 0. Right? So anytime that you want to find your maximum or mins, the derivative there is going to equal 0 because there is no rate of change. So if I'm a bird, right, and I'm flying and I'm getting higher and higher and higher, there's some point where I stop flying higher and higher and higher for like an instant, and then I start going down. So there is no rate of change. There's no velocity happening. All right, so we're going to set f prime of x, or our derivative, equal to 0, and then we're going to solve algebraically. Are your estimates in part C close to those exact values? Okay, so I'm going to take my function, set that equal to, so I have a quadratic here. So I guess my options for solving this quadratic algebraically would be, let's see, the quadratic formula. And potentially I could do some factoring, but I don't think that's going to work because that's going to be 12 and 9. That won't work. Yep, I already did that one. So I don't think that's going to work. So if you use the quadratic formula, you're going to need your calculator anyways. So instead of doing that, I'm just going to go ahead and graph it and then find my zeros. If I'm allowed a calculator for my quadratic formula, I should be allowed a calculator to graph it. I need a better window. So I'm just calculating my zeros. So one of my zeros was x is approximately 2.4. Oops. Okay, that's one of them. And then I'll do my other one. And 4.8685. Okay, so those are my two x values, where my derivative is set equal to 0, or in other words, the slope of the tangent line is 0. And let's see if they are close to my approximation. So the first one was 2.4648, and I approximated it at 2.5. That's super close. And the same with this one, 4.8685 is really close to 5. I was a little bit more off on that one, but close enough from the graph that I was given. And all you have left is your summary.